Thank you. Can everybody understand me well? Even those people in the last rows, great. As you will certainly have noticed already, I'm suffering from a bit of a cold. I will do my best to make that not influence the quality of the presentation, but should you not be able to understand something, then please just give me a sign. Ideally, that sign would not be throwing a bottle after me, but we'll find a way. Great. So I'm here today to talk about Ceph. Quick introduction of myself first. Who am I? My name is Martin Loschwitz. I've been living in Vienna for the past 8 years. Just 2 weeks ago, I moved to Berlin, to the beautiful city of Berlin, actually. It really is. I was not born in Austria or in Berlin there. I was born in a small village not too far away from here, around 100 kilometers to the, west, actually. You may have read some articles I wrote. I've been a fairly active tag writer over the last 13 years. I'm a Debian developer, so I have been working on Pacemaker and chorusing for Debian. I have been writing more articles on tech stuff, and just 2 weeks ago, I took a new position with a company in Berlin, and at Sys11, I'm mainly working as a cloud architect, dealing with topics such as OpenStack and Ceph. That's my hobby, so if someone of you is in Berlin and wants to throw a ball, please don't hesitate to get in touch. And today we're here to talk about scalable storage. We're talking about backups. Obviously, the demands for storage increase almost every year by 100%. We need to store more and more stuff. And we need something that actually can hold all the data that we want to store. And this is where scalable storage comes in. Well, I'm pretty sure that most of you have a clear understanding of storage and scalability. I would still like to emphasize on scalability a bit, basically because that's what we'll be dealing with all the time. And you will certainly all have heard scalability. Who has not heard the term scalability in IT context? Who has? Who's too lazy after lunch to get his hand up? Okay, excellent. Great, just making sure I'm not making something wrong. Excellent, great. So the first part of the presentation is basically going to be a description of Ceph and how Ceph works and what Ceph does internally, whereas the second part is going to be about the question, how can I integrate Ceph into my backup scenarios? How can I actually use this piece of software to store information that my backup software may be producing? How can I access the Ceph cluster, the Ceph storage from the outside? Ceph is about scalable storage, and scalability actually comes in 2 dimensions. First, we have Scaleup. Scaleup is all about increasing the amount of hardware in machines we already have, or replacing machines we already have with bigger ones. The important part about Scaleup is that, in fact, I have one machine before I scale this setup, and even afterwards, I will still have one machine. The machine may be bigger than the one I previously had. It may be able to provide more resources than the old one did, but the important thing to understand is it's still one machine. And Scaleup comes with a serious issue, and that serious issue is that at some point in time, I will basically reach the limits of what is physically possible, because I cannot attach more disks to any arbitrary computer. At some point, I will reach a limit of the controller. At some point, I will not have any available slots in the server to add more hard disks. And that means that just by scaling up the storage system, at some point, I will reach a point where I cannot continue to do that, which would mean I would need to get a second storage. I would need to get a third storage, depending on my needs. And that actually eradicates one of the big advantages that centralized storage brings into data center installations, and that is a single point of administration. In contrast to Scaleup, the principle that has dominated IT over the last few years is Scaleout. Scaleout means that I will not have to add more hardware to existing machines. I will not have to replace existing machines with more capable servers. But instead, what I'll do is I'll just add more machines to my installation. So I will have one server before I scale my installation, and afterwards I'll have 3. Or 5 or 10 or 200, or however many I may need in order to cope with the loads my setup is producing. Which in fact means that if the software helping me to scale out is written in the right way, I can do this infinitely. I can just add as many machines as I may have to in order to cope with the loads that my setup causes. Scaleout is pretty hip. As you will see, as you will have noticed already, almost all modern software pieces support Scaleout. Web servers are a perfect example. We've been doing Scaleout for web service for 20 years now, because really what we've been doing is we've been doing load balancing. And load balancing is all about Scaleout. I would just have a server, and if the server cannot cope with the load that I'm producing anymore, I will add more web servers, and the load will automatically be distributed over those servers that I have. Databases have started to support Scaleout over the last few years. MySQL by now has decent Scaleout capabilities. PostgreSQL has it. With MySQL, we are even one step further by now, because we have installations with Galera that can actually serve in a multi-master mode. So we're even away from the old typical master-slave replication thing that we had. By now, we can do multi-master replication with Galera and MySQL. For storage, however, things haven't been as happy and as great over the last few years. That's particularly because block storages cause a very obvious problem. A block storage device isn't usable in a logical way if you buy it. If you go to any computer store and buy a USB stick, you will not be able to use it in a meaningful way. You could actually write down something onto it, but you would have to read out the complete stick again afterwards in order to get the information that you're particularly looking for. File systems help us to work around this issue, because file systems make block storages organizable and usable in a meaningful way. The problem is that most Linux file systems, in fact, are very closely tied to the block storage that they reside on. So I just cannot take the file system here and split it into multiple parts and distribute those multiple parts over a number of arbitrary hard disks in my installation, because that would necessarily corrupt the file system and my data would be lost. Which means that I cannot create distributed installations using standard Linux file systems, and that's bad, because if I want to create scale-out installations, I need to distribute the stuff that I want to do. And this is where object stores come in. Object stores follow a very simple principle, and that principle, in fact, is that they convert every piece of information that is uploaded into the store into binary objects. And the big advantage binary objects have is that I can actually split them in any way I want to split. As long as I put them together in the same direction that I have split them into, I will get exactly the same file. So if I upload this one file to my cluster, and that file is 16 megabytes large, I can divide it into 4 binary objects. I can distribute those objects over an arbitrary number of disks in my installation, and I will still be able to get exactly the same file out of my block storage again, as long as I put them back in the right order. That is what object stores do. Object stores add an arbitration layer between the file system and the hard disks and the actual user interface. They organize themselves based only on these binary objects. And this is where we start talking about Ceph, because Ceph by far is the most famous object storage implementation out there right now. In fact, that is a fact supported massively by Red Hat, having bought the manufacturer of Ceph around 3 months ago for roughly $180 million United States dollars. And that is something that definitely got Ceph a lot of PR. But let's take a look at the technical backgrounds of the solution. Who of you can guess what this red circle thing is supposed to be? It's an octopus. Actually, it's an octopus. And if you ask yourself what's the name, what is Ceph actually meaning? Ceph is the acronym for the animal family of the cephalopod, which is ancient Greek and means kephas, which is the head, and podos, which is the feet. So these are head feeders, and as you can see, except for a head and feet, these guys don't have anything, which makes the name pretty appropriate. Actually, this is the favorite animal family of the guy who wrote Ceph, Sage Well, and Sage decided to adopt this name for the storage solution that he started to work on around 10 years ago. Ceph isn't as young as many people think, but only after Inktank started to promote Ceph around 2 years ago, the thing got massive PR, and people started to realize that Ceph is there. As we will see, Ceph really is a combination of a collection of tools. So Ceph is not one individual thing, but in Ceph we have a number of different components, and every component plays an individual important role, even when it comes to taking backups. We need to start with the most important component, and in this case, the most important component is called RADOS. RADOS is the object store itself. RADOS is an acronym. RADOS stands for Redundant Autonomic Distributed Object Store. Object store because that is what it is. That is what it does. It stores binary objects. Distributed because it stores them in a distributed manner, so I can shatter my binary objects across an arbitrary number of hard disks present in an arbitrary number of servers. Autonomic because the cluster supports a number of self-healing and self-automation features, so as long as the cluster can physically recover from any outage, such as failing disks, it will do that, and you will not have to get up in the middle of the night just to fix a hard disk that may be threatening the security of your data or your backups. Redundant, in fact, because Ceph is inherently redundant. So any piece of information you store inside RADOS will be stored in a redundant way. And you will not have to do any additional measures to actually get redundancy. That is integrated out of the box. Ceph is made, or RADOS, in fact, is made out of two components. First and foremost, we have OSDs. OSDs are object storage devices, so hard disks. Anything that can take binary objects in Ceph can become an OSD. Any block device that can take a file system which supports user extended attributes can turn into an OSD. If we want to paint in OSDs here at this level of the object store, in fact, they would be down there where you can see the file systems and the hard disks. So we would have these gentlemen down there as our OSDs. The important thing about Ceph is that Ceph exposes unified storage to the users, which means that as a user or any arbitrary client, you will not have to care about the structure of the cluster. In fact, you don't have to care about failing disks at all, because that is something the cluster will take care of. The cool thing about OSDs is that you can actually design them in a way that is completely arbitrary, so you will not have to follow any particular layout. You can have 7 OSDs inside your cluster, or you can have 14 OSDs, or you can have 28 of them, or 3,689. In fact, the theoretical limit is, I think, somewhere at 274 billion hard disks, which is going to cause you additional problems before you actually reach that limit. Unless you're the Lawrence Livermore National Laboratory, these are the guys building nuclear bombs. If they need more space, they have ways to get that. But let's not have that discussion right now. So we have binary objects here. You can have 14 OSDs, and even better, you don't have to follow a special physical layout when it comes to having these in computers. So you can have 7 nodes having 2 disks each, or you can have 4 nodes having completely arbitrary numbers of disks per server. You can, at any point in time, add additional machines with additional hard disks. You can add hard disks which are larger than the ones you previously had, and there will have ways to configure Ceph in a way to cope with that fact. Monitoring servers are the second important part of RADOS. Monitoring servers do 3 different jobs. They take care of cluster health by employing a Paxos algorithm. They take note of all monitoring servers present, of all OSDs present, and they take maps of these devices. And the third important thing they do is they deliver these information, the OSD map and the mon map, to clients connecting to the server. Any client who wants to talk to any of the disks can actually do that, but in order to figure out which OSDs are present in the cluster, the client needs to know which current status the OSD map has, and it can get that information simply by connecting to one of the monitoring servers. If you want to paint those in, monitoring servers are something at the side. They are not actually involved in storing data, but they are very important for the health of the cluster nevertheless. How does data placement in Ceph work? Let's take a look at that. We have 4 hard disks here. Of course, in real-world installations, you will have dozens or even hundreds of hard disks. It's completely okay to have a Ceph cluster built out of several thousand hard disks. You've seen that, and it works actually, so there's no problem with that. But having 1,000 disks on the slide would have made the thing a bit crowded, so we'll work with 4 for the moment. And in addition to our disks, you will see that there is a gray shadow. I will come to that gray shadow in just a minute. And no, it's not about 50 shades of gray. I've had people asking me about that. It's not that. Let's not get into that. We have monitoring servers in addition to that, and we have a client. And the client wants to store information inside our Ceph cluster. So the first thing the client needs to figure out is, what are my OSDs? What disks can I actually write to? And it can do that simply by connecting to a monitoring server and ask the monitoring server, hey, I need a list of the currently existing disks inside this cluster. The monitoring service will deliver that disk as soon as the client knows which OSDs we have. The gray shadow on the disks disappears because now the client has an idea which OSDs he can use to store information. For the sake of easiness, let's again assume that the file the client wants to upload has 16 megabytes of size. The client will now split this 16 megabytes large file into 4 binary objects with 4 megabytes each. That is because the default maximum limit for a binary object in Ceph is set to 4 megabytes. You can increase it, but it's okay to leave the value at the default. And after the client has split those binary objects, it will actually assign the individual binary objects to groups. In this case, the green group and the blue group. These groups have names inside Ceph. They have a special name. These are called placement groups. And they're special because binary objects belonging to the same placement groups always reside on the same disks. So all binary objects belonging to the green placement group here belong to the same OSDs for the initial copy and the replicated copies later on, and the same goes for the blue placement group. And as soon as this conversation, or actually as soon as this calculation has happened, the client just starts uploading. And this is where stuff gets interesting for those of you wanting to use Ceph for backups. Because in fact, the client uploads the binary objects to a number of several disks, and it does so in a parallel way. Which means that you can write from the client side to many, many spindles at the same time. Which means that you can get a very high throughput value for your disks without having to buy expensive SAS disks. You can just buy normal serial ATA disks, and you will still get very high throughput values because you are writing small binary objects to many spindles at the same time. It's completely okay to have Ceph clusters built out of normal standard serial ATA disks. You don't need any high-performance SAS disks for this. You can get the same throughput at no problem at all. Which obviously is important if you want to create a really big backup storage, because you will need much and lots of very cheap storage space. And using the Ceph, you can get exactly that type of storage space. We were talking about replication earlier. We have this status right now. As you can see, there is no replication happening at this point, because right now, if the first OSD or the third OSD fails, then we will have binary objects which are not present anymore. However, as we already said, redundancy is inherent in Ceph. So in fact, as soon as the OSD number 1 here in this case realizes that binary objects were uploaded to it, it will automatically start replicating them to the second target OSD. It will copy them just as well as the third OSD will copy the blue placement group to a second OSD. And this is what the actual result looks like. We have replicas of the binary objects. We have uploaded stuff in our cluster. And only at this point, the client gets the acknowledgement for the write. So at this point, the client understands that we have properly replicated the information inside of our cluster, and the write to the cluster was actually successful. Let's jump a quick step back to this part here. How does the client actually know that the blue placement group needs to go to OSD number 3, and that the green placement group needs to go to OSD number 1? For this part of the job, the original author of Ceph, Sage Weil, has written a separate algorithm. And that algorithm has a name. It's called Crush. Now, it's certainly an improvable idea to name an algorithm that deals with data, Crush. But in this case, calm down, please, because again, it's just an acronym. Crush is the acronym for Controlled Replication Under Scalable Hashing. The cool thing about Crush is that it's a pseudo-random algorithm. So in fact, it will produce random results for individual binary objects, but it will produce them in a reproducible way as long as the design of the cluster hasn't changed. Any problems?
No, that was a very nice way of putting it.
Okay, sorry. Right, we have Crush, and the cool thing about Crush, as I already said, is you can actually rely on the results. So as long as you have the same amounts of hard disks in your cluster, the result of the Crush calculation for a binary object is going to be the same. Only once the cluster layout changes, and only if that change affects the actual Crush calculation for a particular binary object, the result of the Crush algorithm will be adapted. it doesn't make any sense to produce a disk as output of the crush algorithm if that disk has just failed 10 minutes ago. I cannot store anything onto it. And that is why in such situations, crush will actually adapt the output of the actual calculation and will ensure that we are writing to... That's what happens all the time. Can you just... Whoop. Thank you. So the important part here really is I can actually influence crush. There is a configuration file that resides inside the cluster that is called the crush map, and I can actually define certain things inside that crush map. I can make Ceph reg aware just by manipulating the crush map. I can assign higher values to individual storage devices. I can assign higher priorities. And I can do a number of different things just inside the crush map, actually influencing the way the cluster deals with storage distribution inside the binary object model. Once I have done that, I can make Ceph reg aware, which is pretty cool because that is a very nice way, for instance, to shatter your different binary objects across 2 different fire protection zones inside your data center, which is pretty cool and comes integrated into Ceph right away. So that is an integral part of the Ceph workflow altogether. The important part for you guys, given that you're all about backup, really is how do we do on the client side? The best object store is worthless if I don't have a way to access it from either within my applications or via any standard protocol that may be available. The good news here is Ceph comes with a number of different interfaces to the user side. We have 3 of them. We have the Ceph block device, which basically allows me to access a RADOS cluster from a Linux machine just as if it was a standard hard disk. We have the SelfObject Gateway, which provides a RESTful API to RADOS, and we have the Ceph file system called CephFS, which is a POSIX-compatible file system, allowing me to access the contents of a Ceph cluster just as if it was a standard Linux file system. CephFS was the original interface that we had. The Ceph block device and the SelfObject Gateway were added later on. By now, however, these 3 components are equally important for the RADOS object store and for Ceph itself. Let's take a look at the Ceph block device. Some of you may know the thing as the RADOS block device, or RBD. RBD comes in 2 different flavors. We have the Linux kernel module, which is named RBD. In fact, what you can do using the RBD kernel module on Linux is you can basically just connect to a Ceph cluster as if it was a hard disk on a Linux system. So what you will do is you will load the kernel module on your Linux client, and inside your RADOS cluster, you will create an image, a so-called RADOS image, and this image will be exposed via the RBD protocol. You can map it using the RBD command on the Linux client, and it will be available as def RBD1, just like any other standard hard disk would be available, which means that you will be writing to the Ceph cluster in the background, but for you on the actual client, it's going to look as if it was a local block device, and you will not notice any difference from writing to an actual local block device present on your machine. The second interface that we have is QEMU-RBD, and QEMU-RBD in this case just is one example, but very important for those of you doing virtualization using KVM. Who of you runs your virtual machines using KVM and libvirt? So quite some. The cool thing about RBD and QEMU in this case is that we have a patch which by now is integrated in the QEMU upstream, allowing you to access a RADOS cluster natively. So what you can do is you can configure the same image inside RADOS, and you can make QEMU use that image inside RADOS just as if it was a local block device, but you don't need the kernel module on the actual client anymore. So you're not going to wait through the kernel just to access the thing. In fact, RADOS is a user space application, and QEMU is a user space application. And from within QEMU, we can easily access the binary objects that we have inside RADOS using exactly this QEMU-RBD backend. Here's an example for libvirt configuration. Those of you who are as happy about XML as I am will now certainly feel inner vibrations when seeing this. But the important part here really is, as you can see, we define a disk, and this disk is using QEMU. Okay, so XML leads to people start dying in my presentation. Should have guessed that. But anyway, as you can see here, we can define QEMU as a disk inside libvirt. And in fact, that is all you need. In fact, once this configuration is in place, you can run a virtual machine. And the virtual machine is going to have RBD, is going to be RBD backed. RBD supports a number of different flash caching mechanisms. I can have write through cache, I can have write behind, write ahead, sorry. So that's all standardly implemented inside the RBD block device. However, what's even cooler about the RADOS block device protocol, the Ceph block device protocol that we have inside RADOS, is the fact that it comes with full support for snapshots. And that's interesting if you want to take backups of your virtual machine, because really all you need to do in order to get a backup of a virtual machine that is running backed by Ceph is this. And obviously, this is also integrated into the libvirt workflow. So if you use libvirt in order to administer your virtual machines, you can use the libvirt snapshot functionality, and it's going to know what it needs to do in order to get a certain and perfect backup of your virtual machine. It's going to be inside RADOS. So in fact, you can do this once an hour, and you will be able to jump back to any arbitrary state of your virtual machine for every backup spot that you have. And this is a pretty nifty and pretty cool way to get incremental backups of your virtual machines. Because really what's happening inside RADOS is RADOS just takes care of the record of certain states of binary objects at the time you took the actual snapshot. So you're not creating 400 gigabytes of snapshot every time you do this, but in fact you only save the state of the binary object at a certain point in time. And if you change any of those, Ceph will only keep those binary objects that actually have changed, which means that this backup mechanism is fairly nifty and helps you saving lots of spaces for your backups. We have the SelfObject Gateway, which is pretty important for those people willing to store information inside the cloud. The SelfObject Gateway is a RESTful API to Ceph. So in fact, a RESTful API allows you to access a certain service using HTTP. You will probably know services similar to this, Dropbox, Google Drive. All these services follow a very similar goal, and the SelfObject Gateway allows you to access a RADOS cluster, a Ceph cluster, by using a standard HTTP protocol. The cool thing is the SelfObject Gateway is compatible with Amazon S3 and OpenStack Swift. So as soon as you have any software that actually is responsible for taking backups and supports either Amazon S3 or OpenStack Swift, you can actually use that software to back up information to the Ceph cluster that is already running in your data center. So if you want to take backups of virtual machines and you want to provide your users with a way to take backups of their own information from their homes, you can actually do that in the same storage. Why would you want to give users a service that allows them to store their information in your data center? Because having your backups in your own basement isn't a good idea. I know that houses typically don't explode or burn down or do both things one after another, but if they do, things start to suck. And if you have heard of Bidel Garbi, who was Debian project leader for a number of years consecutively, you would probably heard that last year his house burned down during a wood fire. And it actually burned down to the ground, so there was nothing left. No hard disks he may have. Actually, he had explosives in his basement because he was running a rocket company, which may have things made worse a little bit. But if you run into this scenario, actually, you will not have anything. And if you allow your users to just back up their information in an easy and comfortable way using any arbitrary standard backup software in your data center, then that definitely is a cool service that your users are likely going to appreciate. The third interface that we have inside Ceph is a bit of a sad story, actually, because this is the only part and the only component of the complete RADOS and Ceph solution that is not officially released as stable for productive use just yet. Many people seem to think that this is the most important component. In my eyes, it's not. What CephFS really is expected to do is, it is expected to allow you access to certain contents of the cluster using a standard POSIX-compliant file system. And the basic mechanism inside CephFS definitely works. So you can actually run this in test mode, and you can do benchmarks against it. The one thing that currently doesn't work inside CephFS is using more than one metadata server at a time. If you want to use CephFS, in addition to monitoring servers and OSDs, you will need a third service that is called metadata server. The actual metadata inside Ceph are stored in the user extended attributes of individual objects. So this is designed in a better way than, for instance, Lustre is, where you have a central lookup server that serves you metadata. If in Ceph you lose a metadata server, you're not actually losing any metadata. You're just losing the cache for it. And the only role metadata servers have is they are supposed to serve these metadata, and they are expected to do that in a parallel manner. So you are expected to be able to run 6 or 7 or 10 metadata servers at the same time, and they would actually be expected to serve individual subtrees of this Ceph installation that you have. That's the one part that's currently not working in CephFS, the way that the Ceph people would want it to work. If you want to try CephFS, feel free to do that, but don't run more than one active metadata server at a time. Plus, since Red Hat bought Inktank, there have been very active plans, and there has been a lot of work to get CephFS out of the door into a stable way, and I would expect this to become production ready within the next month, certainly. Although I've been doing the same thing during a presentation I said a year ago, but this time I'm really comfortable it's going to actually work. Really, really, really. Right now it's still beta though, so the only thing the Ceph offers guarantee you is that they don't guarantee for anything. Now, if you don't like any of these interfaces that I have just mentioned, if you have an application that is highly specialized in doing something, then you will certainly know what the best way for this application to make backups would be. The good news is, in Ceph we have a binary, we have a library that is called RADOS. You can actually access the contents of a Ceph cluster from within your application using librados. So you can just link your application against librados, and you will then be able to access the storage natively from within your application. There's also a large number of language bindings for librados available. So we have script bindings, for instance, for Perl, of course, we have Python. We even have a PHP RADOS, which may sound a bit absurd to you in the first moment. In fact, it's not though, because if you imagine what many companies running websites do is they run image hosting websites or something like. So what they have is they have lots of images they need to serve the customers. Every image is a binary object anyway. It already is a binary, so you don't even have to convert it. And if you have a way to access the Ceph cluster from within your PHP application, you can actually just serve the binaries out of the clusters, out of the storage cluster, and you wouldn't need to go through a POSIX-compatible file system like NFS or something, which most applications do these days, which, however, doesn't bring any advantage to these setups worth mentioning. Ceph is available for all distributions, for all major distributions out there. Packages are provided for Ubuntu and Debian, and of course, for SUSE and Red Hat by the upstream themselves. So we have a full support for Ceph. On the Inktank side, they are actually delivering packages for all of these distributions. If you ever plan to run Ceph for OpenStack, that's a good thing too, because there's a native integration between the most important OpenStack components in Ceph, even for the backup side of things. And with that, I think I spoke enough for now, and I would like to hear your questions about it, because I guess there will be some.
All right, thank you. Any questions?
Yes, please. Depending on how you have structured your setup, yes, please. First of all, there is an authentication layer in Ceph. So you do have something inside Ceph that allows you to give access to certain users or not. However, you typically don't expose that layer directly to your users. Because what you do is, in libvirt, you wouldn't want your users to access the storage directly anyway. Using the Amazon S3 gateway or the OpenStack Swift gateway, the RADOS gateway, you have a built-in user management mechanism in the RADOS gateway, which can use different backups, such as local authentication or LDAP or something like. So you have a number of different ways to do that. It needs to be a part of your design decision, though. So you need to think about user authentication before actually implementing Ceph. Yes, please.
Just to comment on that,
you actually can do the Ceph export, the authentication part for the file system, yes. So you can expose several different Ceph FS file systems to different users, and only certain users will be able to mount that part. Well, the interesting question here in this case that I would like to ask first is how would you design that? So what would be, okay. So let's start with a 200 terabyte Ceph cluster, which is a very small size to start with. Not sure you would want tapes in the background of that. As long as you can do something to use a tape as a block device in the system, Ceph will be able to use that for OSDs, but it wouldn't really make sense. Typically, a Ceph cluster is expected to grow to a size where you wouldn't be willing to change tapes or anything like that. The interesting part about backing up Ceph is, or actually the interesting part about Ceph and backups is that obviously in order to take backups of Ceph itself, you would need to have another Ceph cluster of exactly the same size. That's not a design flaw of Ceph though, that simply is a problem of if I want to back up 2 petabyte of space, I need 2 petabyte of backup space. So tape integration right now, I would say, doesn't really make sense to go with Ceph. The general expectation is if disks in your Ceph cluster fail, and they will, because you will have lots of them, and they will be failing at a certain point in time, the self-healing strategy of Ceph should be enough to give you enough time to just replace the failed disks. And using that, as long as the cluster doesn't burn down completely, you're fine. If it does, okay.
And somehow caches these objects so you can online access, see my online access things stored on tape. So inexpensive offline storage, which is see my online, and you can access it like online storage.
Okay.
Because it's against the principle of really fast storage, but you have a lot of storage and
but that is not integrating to Ceph, is it? Because I didn't hear of that. Yeah, I mean the thing.
There's a product that
Yeah, one thing that I would definitely want you to take out of today's presentation is Ceph is not the object store. Object stores are just technology, and there is a number of different object stores out there right now. They are all tailored to a specific use case. Ceph is the one that tries to cover as many use cases as possible, but we have a number of different other object stores actually tailored to very specific needs. And depending on the thing you want to do, just like the tape storage thing, you definitely want to take a look at what actually is there. The main purpose of Ceph really is provide huge amounts of cheap online backup storage. That is what one of the things is you can do with Ceph. Easily accessible online backup in a way coming with as little obstacles as possible. Yes, please. You can take out disks at any point in time, of course. Well, I guess if you take out 100 disks out of a 110 disk cluster, then that's going to be a bit of a problem. Obviously, what you would want to do is you would want to take the disks out one after another. So remove the first disk, wait for the cluster to self-heal. That's the way you would do it. You wouldn't even have to take the disks physically out. What you could do is you could tell Ceph OSDs 1 to 10 are gone now, or are supposed to be out of the cluster. Please start re-replicating the stuff that is on it, because obviously Ceph needs to meet its replication policy. And once it's done, you will see that the disks are not in use anymore, and then you can just remove them from the cluster. Yes, please.
Is there a way to design something like storage-to-storage replication?
Yeah.
Completely separated stuff?
Yeah. There is an approach to that, and that approach is using the RADOS gateway, so the Ceph gateway. In fact, it's not as seamless, though, as, for instance, a replication using DRBD would be between two sites. Ceph has always been designed in the beginning to be a synchronous replication solution, and only right now, given that Ceph has by now gained a lot of commercial interest, Inktank has started to think about asynchronous replication of to third sites. So that is being worked on. Right now, there is a setup that you can use to do that, where you have synchronization agents running on both sides of your setup, and they will be copying selected binary objects from one place to another, but that is not transparently integrated. The gentleman in the last row. Yes, there is. Starting with Ceph 080, there is a basic support for tiering inside Ceph. Typically what you do inside Ceph is you have two places where you put SSDs in. Every OSD has a journal. That journal works exactly like a file system journal, and by putting that OSD journal onto an SSD, you can actually just improve the speed and the throughput of your write access to that OSD massively. And the second thing you can, of course, do is you can do tiering. So you can define for individual amounts of data that these are expected to be hot and that you want them to be on fast storage. And after a defined pattern, they will be migrating off to slower storage, to cold storage, so to say. Well, that's a very cold storage. Yes, please. The bigger, the better. Yeah. The network requirement is like this.
Because I can see how you eradicated the limits for storage space.
Yeah.
You just have new nodes.
Yeah.
But network is another matter. And I think you will hit the limit there rather fast.
Well, at SysEleven right now, we are constructing a Ceph cluster, and actually do expect to be doing 40G. Which is not that expensive anymore, at least not expensive as it used to be. Depending on the workload that your cluster is exposed to, you'll be fine with a bonded 10G E-link, so 20G should be fine.
I guess we can do one more question, but then we are a little running out of time right now.
Hey, you started 1 minute late with me, so
okay,
we still have
I
1
grant
minute
you another
15.
minute.
2 questions.
Okay.
Go ahead, please.
The question is the future of SelfObject, actually, because one of those rather disappointed.
Yeah, the future of...
Because we are now using GlusterFS or something.
Okay.
For the backup.
Yeah.
And we also
Well, if I was you, and if I was using GlusterFS, I would be caring less about the future of CephFS than about the future of GlusterFS, but that's a different topic. To be honest, I think CephFS is going to be stable in a certain amount of time, because Inktank has not bought this piece of software just to spend money. They are going to, you know, my opinion is, and that's just my opinion, so nobody write a news entry, and I mean a gentleman in the last row right there, Loschwitz saying Red Hat to abolish GlusterFS. No, that's not the point. What I think is that probably at some point in time, Red Hat is going to concentrate on Ceph and will probably invest less into GlusterFS. But that's only speculation. I have no clear idea about that. And the last one. You can actually use Ceph, the object store, as a backend for HDFS if you want to do that. That's possible technically. So you can actually use Ceph as a replacement for the actual Hadoop storage engine if you want to do that. That's possible by now because there was a patch available and that's integrated into Ceph by now, so that works. Again, thank you very much, and I'm just willing to go away now before they start throwing things at me as well. And have a pleasant rest of the day, and thank you again.
Thank you very much.